astrobiologist and geobiologist studying extreme environments for life. Professor Amy Williams's domain stretches far beyond Earth to Mars, Saturn's moon Enceladus, and Jupiter's moon Europa. In particular, as her official bio describes it, her work is leveraged to study habitability and the search for life on Mars with the NASA Mars Curiosity and Perseverance rovers, on which she serves as a science team member. It was as part of that her and her team's discovery of seven carbon containing molecules found for the first time on Mars that has excited the scientific community. To understand whether the discovery signals potential for life on Mars or indicates something else, MCR spoke to Dr. Amy Williams. Welcome to Mayank Reports, Professor Williams. It's a great pleasure to have you.
Thank you so much for this invitation. I'm so excited to be on here.
And many congratulations to you and your team on the discovery of some remarkable carbon-containing molecules on Mars.
Thank you. It's fun to say I led the team, but it would be a lie to say that it is not a huge team effort to get something like this accomplished.
I'm sure. I know science is not done via the gut, but what's your gut feeling about the seven molecules found for the first time on Mars? Do you think they are biologically produced or geologically produced?
I'm going to say neither, actually. I think that they are produced in the interstellar medium on meteorites, at least some of these. And that's the direction the paper has tried to direct most of our evidence in that sort of interpretation, that this is material that rained down on Mars billions of years ago in the ancient past. And so it's exciting, of course, to find something like this on Mars. I think it's going to take extraordinary evidence to say that we found evidence for life with any type of mission. And so, I feel like this is a stepping stone in that story. It's certainly not pushing us toward a biologic interpretation right now.
I see. I was not expecting this interesting segue because I've done a lot of interviews related to panspermia, something which Fred Hoyle and others founded. Do you think it's in a sort of way indicates something of that nature? Because if it rained on Mars, the way you're describing, the life has been seeded. That's the belief in panspermia. So Dr. Vikramasinghe, who is again a very eminent astrobiologist based in the UK, who pioneered it along with Sir Fred Hoyle, it is their conviction for decades now, 6 decades now, that panspermia is the cause of life, not just here, but perhaps across the universe. What's your view on that?
So panspermia is the concept that life could travel on meteorites that are ejected from other planetary surfaces, that they enter into the orbit of a solar system, they orbit for a while, and then they happen to land on another world that would be conducive to them effectively reanimating. I'm not a panspermia expert. When I teach astrobiology courses, we talk about that as an idea or a concept for what would it take for life to survive each of those steps, to survive being ejected off of your home world, to survive from whatever your environment on a planetary surface was in the vacuum and cold of space for tens of thousands of years, perhaps, and then to survive reintroduction on what is to that organism an alien world that may or may not have the conditions conducive to that life. So I know that there's been many, as close as you can get to doing comprehensive studies, you can study how organisms might survive ejection, how they might survive reentry, how they might survive tens of thousands of years in orbit. So, there are components where life can find a way in each of these. Obviously, it's not demonstrated that this can go from start to finish with those organisms surviving. So it's a very interesting concept that doesn't have, it doesn't have proof yet, right? If you don't have evidence for life beyond Earth. There's so many compelling ways that you could have an origin of life on Earth that it doesn't necessitate the concept of panspermia, but I think it's a very interesting alternative or way to think about how life might find a way.
Yeah, Dr. Vikram Singh's opinion has been, like I said, he has featured on my show several times. He believes that life's building blocks have come via that route. But anyway, I think we are digressing here. One interesting fact that jumped out at me from your work is that after billions of years of exposures to Mars radiation, these molecules haven't broken down. Do you wonder about that? Why that happened?
Oh, yes, absolutely. So what we think has happened is that the organic carbon we detected, we used a first of its kind experiment on the Curiosity rover. This experiment it's the way that it works is it takes complex, large, what we call macromolecular carbon, and it can break it down into its constituent parts. And that's what we observed and reported on in the study. And so we think that it's a combination of it being this large macromolecular carbon that is actually a bit more resistant to radiation processing. But the other thing is that this material was not always at the very near surface of Mars. In Gale Crater, we know the crater actually filled all the way up with sediments. And then a lot of that sediment has been winnowed down into the central mound and kind of the lowlands that you see around that in Gale Crater. So there was an overburden of rock in the past that would have protected this material. Now, we don't know how long ago that material eroded away and, exposed the rock that we ended up drilling with this mission. But it is not the full, 3.5 billion years. We don't have great constraints on that time frame. But it wasn't that whole time. So we think it's a combination of both of this recalcitrant material that can survive in the near surface, as well as the fact that we only saw this material exposed at some point in the geologic past. And so it had some protection from the radiation environment.
I see. If life did indeed occur on Mars at some point, it wouldn't be as if these molecules are necessarily evidence of that if they came from elsewhere, right?
So yeah, the molecules we saw are very, in the grand scheme of things, quite small. And so they are, the suite of molecules we saw is what leads us to the interpretation that at least some of them are maybe meteoritic, delivered by meteorites. But they're so small that they're the kinds of things you would see made by geology, made on meteorites, or breakdown products from life. So you can't assign an origin to it because they're so relatively simple.
I see. You have also called the detection of nitrogen heterocycles profound because
Yes.
these structures can be chemical precursors to more complex nitrogen-bearing molecules. Please elaborate.
Oh, yes. So one of the exciting findings, of course, I think it's all exciting from this paper, but one of the things I didn't necessarily expect is that we have indications of what you described appropriately as a nitrogen heterocycle. So what does that mean to your audience? That
Right.
means that carbon can form ring structures. And so you can have 5 or 6 carbons in a ring all bound together. In a nitrogen heterocycle, there is a nitrogen in place of one of those carbons in the ring. And so what we found is a molecule that's probably related to something called an indole. So indoles are really interesting because they are one of many precursors that play a role eventually in the formation of DNA, the genetic material for all life as we know it. It's not evidence for broken down DNA, it's not evidence for life, but it is an indicator that prebiotic chemistry, the chemicals that we expect might have led to an origin of life on Earth, the things that life as we know it use, those molecules are present. And so this is profound, I said, because we actually have not seen evidence for a molecule of this class, a nitrogen heterocycle, on Mars before. I don't even think that there's concrete evidence for them in Martian meteorites. I think there's hints of them, but we've potentially not yet detected them. I think the literature is rapidly evolving. So if I'm not quite up to date on that, my apologies to those authors, they can correct me. But it's exciting because we're seeing more and more of the building blocks for life as we know it present on, a neighboring world. And this is really exciting in trying to understand, could an origin of life have occurred on Mars? What does it mean for the rest of our solar system or our galaxy if you have these really common molecules present throughout? Does it give us more of a hint that maybe there is life out there?
Right. Somewhat of a tangent. The fact that a mini lab called Sample Analysis at Mars, or SAM, located in Curiosity's belly, can perform wet chemistry, that is, being able to drop samples in a solvent cup, is considered crucial. Tell me some more, because I'm quite fascinated by the fact that 90 million whatever kilometers away from us, a little rover can perform that. It's astounding.
It really is. And I think for the chemistry community, this has been a really fun story, because they said, we didn't know that you could do wet chemistry on another world. We've actually done wet chemistry experiments, which, as you appropriately described, is taking a ground sample or a powdered sample of rock and delivering it into a little cup that contains a chemical in it in a solvent. We carry 2 of these types of chemicals on the SAM instrument on board Curiosity. We've performed a few experiments with the first chemical, but the study that we're talking about today, this is the first time that we've used that second chemical. It's called TMAH. It stands for tetramethylammonium hydroxide. But beyond the long name, it's just really useful for breaking apart large complex carbon into basically bite-sized pieces that the instrument can detect. And I can say, in labs on Earth, we like to use a lot of solvents to extract organics and learn about their character. And this is a little bit of a quick and dirty method almost to be able to do that. So you want to make autonomous as many of the steps as possible. And so by being able to just deliver sample to a little cup, as opposed to adding solvents and shaking them and decanting them, that's a whole thing that really, at this stage, it might take humans in the loop to get that to happen. This is a really great way to start to get insight into organic carbon that's present on other planetary bodies that we simply couldn't see with our existing techniques.
I see. How long have you been involved with Curiosity mission?
So I actually joined Curiosity before we even launched. I joined as a graduate student in 2009. I stayed on through my graduate career, through my postdoctoral research, and I'm now a participating scientist, still with the SAM instrument team on board the mission. So I've been on since before launch. It truly almost feels like a one of my children at this point. It's that really. It's a relationship that you don't expect a person or people to have with a robot, but it truly does feel like that relationship.
Indeed, I'm sure it does. There is a gentleman called Dr. Ashwin Basavada, who is a mission specialist on. I thought of him because you mentioned that. Do you ever communicate? Are you in touch with him at all?
Yeah. So Ashwin is our project scientist for the mission. He, of course, has also been on the mission since before we launched. Ashwin has been an integral part of getting this experiment, like explaining to NASA why it was important to do, helping us to prioritize where to perform the experiment on Mars and within Gale Crater. Ashwin is an incredible scientist and an incredible leader for this mission. So I'm thrilled that you know him as well, because he's good people and he's an awesome scientist and an awesome lead for this mission.
He was one of the first people to feature on my channel as well. Do you think we are reaching a stage in history where the breaking news will not be that there is life elsewhere in the universe, but that there is no life elsewhere in the universe?
Ooh, that is tricky. And I do think about, how would we communicate if we did find irrefutable evidence for life beyond Earth? How do you communicate that responsibly? How do you communicate it with, X% of the community supporting the interpretation, or if there are people who don't yet support the interpretation, why? It's really challenging because, you don't necessarily want everyone to jump on the bandwagon and agree. You want that critical scientific thought. You want the scientific method to play out and to be able to test alternative hypotheses if they exist. So when it comes to searching for life on Mars, I think a lot about, if we do find that evidence for life, that's profound, of course, because it would demonstrate that there was life on one of our nearest planetary neighbors, in a solar system where we know at least there's one other data point, ourselves and the life that has existed on Earth for billions of years. And you can extrapolate that to consider there's the possibility for so many more potential habitable and inhabited planets out in the galaxy and in the universe. On the other side, if somehow we were able to say definitely there was never life on Mars, which I think it would be very challenging to demonstrate that, but say if we did, that also presents these extraordinary questions about why would our nearest planetary neighbor that has a very, that's had the same rocks raining down that formed these planets. It had water, it had, it has gravity, it had a magnetic field. It was so Earth-like in its infancy as a planet. Why would you not have life evolve on there as well? And so I think these are all very compelling questions. And so I don't know what that tipping point is of one over the other, but there's certainly, I think, a profound aspect to asking these questions and to conducting these searches, because I think finding evidence for life beyond Earth would be one of the most important discoveries humanity can make to sort of understand our place in the universe, who we are, how we are treating our home world, how we treat each other. I think all of this gives us a different framework from which to consider humanity and life as a whole.
Indeed, indeed. I want to flip the scene a bit. Imagine a situation where the kind of life we have on Earth had existed instead on Mars, and you were looking at Earth to detect signs of life. All things being equal, what would have jumped out at you looking at Earth?
That's a great question. If it's the Earth of today, seeing so much water on the surface, in a liquid form is that would be incredible to find on another world. And we have seen liquid water oceans on some of the icy outer ocean moons in our own solar system. As far as we understand, water is the universal solvent for life as we know it. So this would be one of the, I think, most promising indicators. Oh, this is a great place to look for evidence of past or present life because of the presence of that liquid water.
Right. As an astrobiologist and a geobiologist, which is a very interesting combination, you study the formation and preservation of biosignatures in extreme environments on Earth. Within our solar system, which other planet apart from Mars would you like to study for those biosignatures?
Ooh, excellent question. So I alluded earlier to the presence of liquid water oceans, for example, on Enceladus or Europa. These are places beyond, so if I have to pick, my next favorite place beyond Mars, those worlds are incredibly intriguing. The concept that you have liquid water oceans, you have some protection from the vacuum of space, maybe from the radiation environment that exists because of the giant planets around which these moons orbit. And then you also have a source of energy in sort of the geothermal interactions of that crust of that world interacting with the ocean. This is one of the environments that we think might have been an origin of life environment on Earth. So it of course, just tickles your imagination to consider what might be under those ice shells out on those moons. Those are the places that I think I'm most interested in exploring beyond sort of Mars and our inner solar system.
I see. Notwithstanding many literary odes to its beauty and its comparison with us as our twin, Venus is utterly inhospitable. Since you study extreme environments, what might you look at if you were to look at Venus?
So yeah, Venus is such an interesting contrast to Earth. As you said, it's our twin, right? It's about Earth-sized. Venus, of course, has this runaway greenhouse effect. It has incredible pressure at the surface that can melt lead. So it's not hospitable to life as we know it on the surface of Venus. But there's been interest in exploring the cloud decks on Venus because there are there are, I would say, sub-environments where the pressure and temperature are actually within the range of even our extremophilic organisms, as well as the chemistry of the clouds, where there are extremophilic organisms that could live in those environments. Now, there's a lot of challenges that we haven't quite figured out how to address. Are these organisms being continually lofted, to stay in suspension in the atmosphere. If they settle too far down, they will be under too much pressure and too high a temperature. So is it possible that organisms could live in those cloud decks? That those are the kinds of studies that people are actively pursuing to try to understand what can life as we know it do, and what can't it do, and can it fit in that box if it had the opportunity to evolve. So there's interest, of course, in exploring that as a potential habitable like sub-environment, but there's also, I would say, a lot of like controversy and a lot of unknowns that make it, it's a neat idea, but there's not anything extraordinarily compelling as of yet to point us in that direction on Venus.
Right. Given our anthropocentric fixation, we imagine life in our own image, as it were. Why is it that? I mean, I'm sure there are life forms which we do not recognize as life forms already out there.
Sure. I mean, even on Earth, we have this challenge. There's this, even we teach biology courses, we have these definitions of what it means to be alive. And something that doesn't fit that neat definition is a virus. And I think that many of us are quite familiar now at this point with how a virus this little tiny feature can impact our lives. And so it's really interesting because even on Earth, we have things that don't quite fit the definition for life, but they're not necessarily not alive. And so it's this really interesting concept that maybe life is actually on a continuum of definition, and it's not going to fit in a neat box the way that we like it to, or we would want it to. And so
absolutely. And in fact, if you extended that logic, the universe itself would be a form of life, the entire universe.
Oh, yeah. Like how you define it, I think, can really impact, how we perceive this. So I do get that question a lot about like on Mars, if we're searching for life on Mars, why do you look for the things that make up life as we know it on Earth? Why wouldn't you look for the example people always give is like silicon-based life? I think they like the idea of going back to Star Trek and like the concept of a horda, And I say first, I'm like, I can't say that it's not there. I haven't found that evidence yet that it is there. But what I figure is, why start, across the field of likelihood and of what we know. Start with what we know and expand out one sigma from that. It also makes sense for a planet like Mars, so close to Earth. Like I said, we had the same materials raining down from the solar system during planetary accretion, during delivery of organics that may have played a role in the origin of life on Earth. If there were life on Mars, perhaps it would have at least a similar biochemistry to that of Earth, because the same starting ingredients were present on both worlds. So that it's sort of a starting point. It's not saying don't look for silicon-based life. It's saying start with what we know and what we know how to study, and then expand from there. And there is a whole field of agnostic biosignature studies that look at patterns and complexity to try to explore how else could you define life without sort of the canonical fields that we've worked with for really centuries at this point. How do you expand that definition? And these are all active fields of study.
Just last couple of questions. One is, what next for you now that this is out of your way? Are you still focused on studying that chemistry, or you're on to something else?
So I would say, as far as this first experiment from the SAM instrument with this particular chemical, I think that there's so much data in this initial analysis, and I think there's more that we can dig into. And so I'm partially sharing my time with maybe digging more into some of the lower abundance features that we see in the spectra. Can we resolve their identities? But I think the big thing about this experiment is that it is a springboard for future experiments with the same chemical on other missions. So this chemical is flying on board an instrument on the European Space Agency's Rosalind Franklin rover, which is also going to Mars, and will be able to drill 2 meters into the subsurface.
Oh, I see.
What an extraordinary opportunity to look for organic matter that maybe hasn't been impacted by the radiation environment at all. And so that's one opportunity. And Rosalind Franklin right now has a ride in 2028, which is it's so exciting. And then this chemical is actually flying on board the Dragonfly mission to Titan. So yeah, the rotocopter mission that's going to go to Titan also has this chemical. And so although we're not searching for life on Titan, Titan is this really, if you want to talk about a truly alien world, they have lakes and rivers of methane and ethane. So it's going from a very geochemically, or I should say like organic matter lean environment on Mars to a place that has, oceans effectively, or lakes of organic molecules, methane and ethane. So yeah, it's such an interesting like comparison of these two worlds, and this chemical is flying on both those missions. So we're hoping the lessons learned from our experiment can lead to more robust experiments in the future with those missions and beyond.
I see. Mars doesn't have plate tectonics, right?
So yeah, if it did, it failed billions of years ago. Yes.
So that, it could have an impact on whether or not life evolved at some point.
So yeah, one of the things we wonder about is plate tectonics and the recycling of basically biogeochemically relevant elements. Is it a requirement for the survival of life over long time periods on a planet? Again, with our one data point, we don't know. But that has been a consideration about, could you have recycling of these important elements on a world in a way that could support an ecosystem without plate tectonics? We don't know. But again, I keep saying the same line, life finds a way. I don't put it past microbes to figure out solutions. They maybe just have different metabolisms, or they metabolize incredibly slowly because their resources are limited. And so I don't put it past a microbe to evolve and figure out a way to deal with it.
To conclude, this is just an aside. It's not a question. I was amused to find the mention of naphthalene among the organics detected in your study. And my mind went back 50 years to, in fact, I got that smell in my nose of the naphthalene balls, the mothballs.
Yes.
So,
no, you're absolutely right. These molecules that people, we maybe don't know the proper name for them, right? The chemical name for them, but you've experienced almost all of these in your life here on Earth, which is really, I think, a nice connection with the reality of like our lives and our existence with things that are happening, millions of miles away.